Propagation of errors. When you make measurements in the lab, every measurement you make should also have an uncertainty, plus or minus something. If you specify the plus or minus thing in the same units as the thing you're measuring, it's called an absolute uncertainty, and we'll use the symbol lowercase Greek letter delta to write it mathematically. An alternative way of expressing an uncertainty is as a percentage or fraction of the thing you measured. This is the same as delta something over the something. This is called the relative uncertainty. So delta something is an absolute uncertainty. It has units. The relative uncertainty is a fraction or a percentage, unitless. Some say error when they're in a hurry, and uncertainty has too many syllables. Don't sweat the difference. So you've measured a quantity, let's call it x, and its uncertainty in the lab. Now you want to use that number to calculate something else. Let's call it z, using some formula z of x. If x might be off by an amount delta x, then by how much might z be off, delta z? The answer depends on the function. Suppose you move over some amount in x, you can figure out how much you'd move up in z based on the slope of the function. The offset in z is the derivative of z times the offset in x. Let's look at an example. Suppose you've measured a velocity, v, and you want to calculate the kinetic energy, k, which is 1/2 mv squared. Suppose that m was an exact number. There's an uncertainty on v, delta v. The uncertainty on k is the derivative of k with respect to v times the uncertainty on v. Now plug in all your numbers to compute not only k, but also the uncertainty on k. Let's make it a little more complicated. Suppose you've measured two things in the lab, each of which has an uncertainty, and you want to compute something by combining the two. For instance, kinetic energy from both a measured velocity and a measured mass. Here's how to put them together. This is called adding the uncertainties in quadrature. What's with those curly D symbols? If you've never seen them before, this is called a partial derivative. All it means is a derivative with respect to one variable at a time. If the regular derivative is the slope of a tangent line, then in 2 dimensions there's a tangent plane. Partial x is the slope of this plane along x, and partial y is the slope along y. They're easy to calculate, just like regular derivatives. Look at one variable at a time, while treating all the others as if they were constant. You already know how to do it. The special symbol just makes it look impressive. So why do multiple uncertainties add in quadrature? Well, each could make your measurement larger or smaller, but you can't know which is doing which. Best case, the uncertainties could oppose one another and reduce the overall error. Worst case, they could add up for maximum error. But if the two effects are random and independent from one another, then the effect of both together could be anywhere in between. Putting them at a 90-degree angle like this represents their average relationship over many unknown possibilities. So the quadrature sum of two uncertainties is less than it would be for the worst case, but greater than either of the individual uncertainties alone. Let's revisit the kinetic energy example again, but this time with two variables. K equals 1/2 mv squared, only this time both m and v are measurements with uncertainties. The uncertainty in k is the two sources of uncertainty added in quadrature. Each one involves a derivative of k with respect to a different variable. Now let's plug in all our numbers. And that's all there is to it. Now this is a lot of math to do over and over again during lab. There are some patterns you will encounter frequently which can be calculated ahead of time. There are tricks and shortcuts. Let's look at a few. Multiplication by a constant. When z is just a constant c times a measurement x, the derivative of z with respect to x is simply c. Therefore, the uncertainty on z is c times the uncertainty on x. So when you multiply a measurement x by a constant, you multiply its uncertainty, delta x, by that same constant. Addition and subtraction. When you construct the uncertainty on the sum or difference of two variables, you'll notice that both the derivatives are really easy. They are 1. The formula reduces to the two original uncertainties added in quadrature. Multiplication and division. Let's again construct the uncertainty on the product or quotient of two variables. The derivatives are a little more complicated, and at first glance the result looks messy. But let's look at what happens when you divide both sides by z. There's a pattern with the relative uncertainties. They add in quadrature. Remember, the relative uncertainty is delta something over the something, the one that's expressed as a fraction or a percentage. This also demonstrates why, if one measurement is much more accurate, relatively speaking, than the other, you can sometimes ignore the relative uncertainty, which is smaller, and treat that measurement as though it were exact. This will save you a lot of math, but be careful. Can you think of an example when this would not be a good idea? What if you're combining 3 or more measurements? One can construct a right triangle in 3 dimensions using the 3 different sources of uncertainty. The hypotenuse is the square root of all 3 uncertainties squared. In other words, just extend the rules that you already know, adding 3 things in quadrature rather than just 2. Of course, this is just a quick introduction to a vast and fascinating field of statistics and error analysis. But it should be enough to get you through General Physics Lab. Good luck!